There are two ways to define trigonometric functions. We can look at them on the unit circle or through right triangles. It turns out that they're similar, but we're going to start with defining them on the unit circle, and then in Chapter 8 talk about them in respect with right triangles. What is the unit circle? Well, the unit circle is the circle with radius 1 unit, centered at the origin. So it turns out that it has the equation x squared plus y squared equals 1, right? Because remember that the equation of a circle, x minus h squared plus y minus k squared equals r squared, where the center is h and k. Yeah. Here is a picture of the unit circle on a coordinate plane. Its center is right here in the middle, and its radius is 1, so we go out to 1 in all directions. Recall that the circumference of any circle is 2 pi r, and circumference of the unit circle then is just 2 pi, since radius is 1, right? This radius here is 1, right? If you plug a 1 in for the r, you just get 2 pi for the unit circle. That's interesting. Recall that 2 pi radians, that there are 2 pi radians in one revolution of the terminal side of an angle, and the circumference of this is 2 pi. How convenient. Now, what we're going to do is we're going to take our unit circle and a line segment of length 1 with its endpoint at 1, 0. Okay, so let's draw a new unit circle. 1, 1, negative 1, negative 1. Unit circle. You guys will learn that my circles are horrible. And I'm going to say, here's a line segment with an endpoint here at 1, 0, and it's going to be about length, and it's going to be exactly, pardon me, length 1, right? This whole line segment, okay? What we're going to do is we're going to take this line segment and kind of think about wrapping it around. So we're kind of, kind of bending it and laying it down here on the unit circle, okay, until it's laying on it. If we look at the angle in the standard position whose terminal side extends to this endpoint here on the unit circle, it has measure of 1 radian, remember? 1 radian. Yeah. Well, we could do the similar thing for a line segment of any length, right? I'm going to choose the length and call it theta. Oops, sorry about that. 1, 1, negative 1, and negative 1. Here's my unit circle. Alright, and I'm going to say, okay, this is an arbitrary length. Okay. I'm just going to make it about that long, and we're going to call its length theta instead of 1. Actually, I'm going to make it a little bit longer. Right? Now if I think of wrapping this line segment, I'm kind of bending it down and bringing it over until it lands here, right? I'm going that way with it. Yeah. This line segment now, this part of the circle now has theta. And if I take a look at the angle whose terminal side lands at the endpoint of that line segment on the circle, I'm going to call that angle theta radians. Yeah. Note that all the way around, if I had a line segment theta that was 2 pi long and I wrapped it all the way around, then that would be 2 pi radians. Okay, so why am I doing this wrapping thing with a line segment of line length theta and talking about the angle? Well, it turns out that the coordinates of this point here, if I call it P, x, y, the coordinates of the point where the end point of the arc, right, this is an arc here, of length theta lands, are the two outputs. So I'm saying that the x and the y here for P are the two outputs of our trig functions, sine and cosine. And it turns out that they actually are involved with all 6. There are 6 trigonometric functions, and they're involved with all 6. Okay, so let's now make a definition. We're going to let theta be a real number. An angle, right? And we're going to let P with coordinates x, y be the point on the unit circle that corresponds to theta. What does that mean? Corresponds. Yeah, it means basically it's the point where one endpoint of the arc of length theta with the other endpoint at 0. Whoa, what happened? 0, 1, I must push the erase button. Quote, lands, right? Then, based on that, we can define functions, what we call the sine function, abbreviated sine of theta. That's defined as the y-coordinate of P, right? So this y here, that's the same as this y. Yeah? And it turns out that the cosine function, which we can abbreviate cos theta, is x, right? And again, the x here is this x right here. All right, now we can go even further and we can define 4 other functions. We can define what we call the tangent function, abbreviated tan theta. Turns out that that is y divided by x, where x does not equal 0, of course. We can talk about the cotangent function, which we abbreviate cot theta, is x over y, where y does not equal 0. Then we have the secant function, secant theta, which is 1 over x, where x is not 0. And we have what we call the cosecant function, which we abbreviate CSC, is 1 over y, where y is not equal to 0. Altogether, these are called the circular functions or the wrapping functions because of how we define them on their unit circle. Okay, we're going to use these definitions of the trigonometric functions to solve a problem. We're going to let theta be a real number. If we have a point P that's 1/2 square root of 3 over 2, that corresponds to theta. And when I say corresponds, I mean what we said earlier, right, about corresponding. we're going to give all values of the 6 trig functions that we defined earlier based on those definitions. Notice that we're not ever going to find out what theta is. This is kind of a trend. You don't always have to know theta to be able to talk about its trig values. Okay, so we know that sine theta then is y, right? And the y value for this point is square root of 3 over 2, right? Cosine theta, which is x, is 1/2. Tangent theta, which is y over x, will be square root of 3 over 2 divided by 1/2. That is the same as square root of 3 over 2 times 2 over 1. The 2's cancel, and I'm left with just the square root of 3. Yeah. The cotangent of theta is x over y. This time we're going to put 1/2 over the square root of 3 over 2. That's the same thing as 1/2 times 2 over root 3, which is 1 over the square root of 3. Now we're not going to leave that radical in the denominator. If you remember, we have to do something called rationalizing it. So I'm going to multiply both the numerator and the denominator by the square root of 3 so that my denominator can become a rational number, 3. Okay? Now I didn't do cosecant and secant, but you can do that. Based on the definitions above, I think you understand what's going on. Yeah?